The question is, how do we differentiate our exponential functions? We know how to deal with polynomials and things like that. Here we go. E to the power of function x, how do we differentiate it? Well, it's the function I'm interested in differentiating. So what we do is we differentiate that. It becomes the coefficient of the function. The one thing I guess we really have to be careful with is that power. Unlike the polynomial we took one off the power. With an exponential we don't. We leave the power the same. It stays as whatever function x is. So we differentiate the power, that's what we're interested in, but we put it out the front. Now if that base is not e, so that's just when the base is e. When the base is not e, so it's a, how do we do it? We do it exactly the same way, but the difference is we multiply it also by the natural log. Remember, sometimes I write log for natural log, but it's the natural log of a. That all just basically comes from change of base. So essentially you're doing it all in one hit. You're changing it to base e, so you can differentiate it, and then you're changing it back to the original base. But we essentially all you end up doing is multiplying by the natural log of the base. The world's easiest calculus question. Maybe. Y equals e to the power of x. Well, differentiate the power, differentiate x, you get 1. It becomes the coefficient and you don't change the power and it feels like you haven't done anything. There it is. Y dx equals e to the power of x. But what's really interesting about that is if you think about what y dx measures the slope of the graph. And so what we're essentially saying is the slope of the exponential curve is always equal to the y value. This explains why that exponential curve rises so quickly. Because as it's going up, the y value is increasing, but then so is the slope. So it goes up quick, and goes up really quickly. So you get 5x, differentiate 5x, we get 5, so it's 5e to the 5x. 4x plus 3, 4e to the 4x plus 3. You get the idea. Of course, it doesn't have to be a linear power. X squared plus 3x plus 2. Make sure you use your grouping symbols, because remember, all of it's multiplied by 2x plus 3, not just 3 times e to the... So make sure you use those. All of our rules that we saw before will now come into play. This is actually now a product rule question. We've got two functions multiplied together. One of those functions is 3x squared, one is e to the 4x. So we write down the first, diff the second, plus write down the second, diff the first, expand out. It is nice to factorise these. Certainly if we're then going to use the derivative to do something, if you have to find stationary points or something like that, it's going to be useful for it to be factorised. Chain rule, anarchy, bring down the power. So 7, lower the power, 6, diff the inside, 3e to the 3x, tidy that one up. Quotient rule, square the bottom, write down the bottom, diff the top, minus write down the top and diff the bottom. And I guess the other thing I should have highlighted, be careful, remember when we multiply we add the powers. It's so easy to look at e to the x times e to the x and write down e to the x squared. No, e to the 2x, add the powers. Just be careful. There are those little silly mistakes we can make when we're working too quick. And tidy that one up. And of course, why did we do it? We wanted to find equations of tangents and things like that. So all right, now we want to find the tangent to this exponential curve at the point 1, and I've used the exact value for the y value, e squared plus 1. So, okay, we find the derivative. That's what measures the slope. That's the formula, that's not the slope, so we sub in the x value, we get 2e squared. Point slope formula, it looks funny, but it is still a linear function, because remember, e is a number. E is not a pronumeral. We still have something there which has two pronumerals, one of those is an x, one of those, that is a linear function. But 2e squared x minus y minus, and the constant value in this case, e squared plus 1. Alright, here's one where the base is not e. But that's okay, we just do it exactly the same, but I will also multiply by the natural log of the base. So in this case, the log of 4. Oh, here we go. Well, we'll look at log functions later, but at this stage, how on earth would you differentiate a log function? Okay, we rearrange the equation. If y equals log x, then I know x is e to the power of y, and now we know how to differentiate an exponential function. So dx dy will be e to the power of y. If I turn both sides upside down, I have the derivative. Okay, it's in terms of y instead of x, but it's all right. I could still find a value there. I just substitute the y value in instead of the x value. But if I really wanted to make it in terms of x, which a lot of times we do, I can do that as well, because look what I got up here. X is equal to e to the power of y. Oh, okay, I could have written that as 1 on x, and there's the derivative. All right. There's our first bit, the differentiation of exponentials.